Hello guys, I hope you all are doing good. I am Vaishali Kikan and we are discussing the VLSI technology. In that we are discussing the process integration, and today our topic of the day is the copper interconnection formation. I hope you all have seen the previous video in which I have talked about the interconnection formation with the help of aluminium and its alloys. If you have still not watched that video, it is highly recommended that you go back, watch that video first and then come to this video. So as I told you, we are moving towards the copper, which is the technology of the future, and a lot of R&D is going on copper as well. So what is the advantage of using copper? There must be some advantage of using copper, and this is the reason we are shifting from the aluminium and its alloy towards the copper. So what is the reason? First reason is that with the help of copper I will be getting higher speed and higher reliability as well. So these two reasons are enough to move towards the copper, right? So the two advantages associated with the copper is its high speed and high reliability, right? So how we are getting high speed with copper? Because it is having the lower resistivity than the aluminium and its alloy. This is the reason it is going to give me high speed. So it is having higher resistance to electromigration also. That is a very big problem associated with the aluminium and its alloys. So we have to overcome this problem as well. So for that I will be using the copper because it is not prone to electromigration problem, right? So these are two very big advantages, and because of this we are shifting towards the copper, right? So it is hard to dry etch and we will be having delayed copper application as well. So we are using the chemical metallical polishing as an intermediate process when I am using the copper as an interconnection metal, right? So chemical metallical polishing was developed and matured in the 1990s, and after that only we were shifting towards the copper, and we were not using the aluminium and its alloys, right? So now R&D is going on. So after the CMP only the R&D started on the copper and we were shifting towards the copper, right? So CMP is a very important process in the manufacturing of the copper interconnection, right? So we will be understanding how it is very important, where it is used in this video itself. So CMP, we have talked about the CMP. It is used in the bulk tungsten removal for the plug formation, right? There I talked about the CMP process. It is used for the planarization of the given surface as well, and it is used for the removal of bulk tungsten for the plug formation as well. So copper process is similar to the tungsten plug process, right? I can say that. So now trenches are etched on the dielectric surface first, right? And after that we are going to deposit copper into these trenches. After that we are going to do the CMP, which is going to remove the bulk copper layer from the surface, and after that we are going to embed the copper lines in the dielectric layer. Now here I don't require the metal etching step. So here we have one metal etching step reduced, right? So now this is how it is different from the traditional process. I'm going to talk about this as well. So here the copper interconnection formation is a dual Damascene process, right? So here we are having the most commonly used method for the copper metallization, right? First of all, I am going to do the photolithography to etch the via, and then I am going to strip off the photoresist. After that again I am going to do the photolithography to etch the trench, and again I am going to strip off the photoresist. After that I am going to deposit the metal, and then at last I am going to anneal it, right, to give me the single crystal structure. After that at last I am going to do the metal chemical metallical polishing. So how the traditional process is different from the dual Damascene copper process? In the traditional process we were having one dielectric etch process and one metal etch process, right? So both of them were there, but in the dual Damascene copper process we have the two dielectric etch. You can see it here. We were having the etch via and the etch trench. So for both of them are the dielectric etches. We are not having any metal etch in the dual Damascene copper process. So this is how The traditional process is different from the dual Damascene copper process. The main challenges of the dual Damascene copper process are the dielectric etch, the metal deposition and the metal CMP. So all of them are very important. We are going to talk about all of them. So you can see we are going to deposit the nitride, then the USG and the nitride USG. So here you can see we have the two layers of the nitride and the USG, right? So here you can see this is the first layer of the USG and this is the second layer of the USG. After that we are going to form the via mask and we are going to form the via holes right here. So we are going to etch the via and then we are going to strip off the photoresist. So this is how the via trenches are looking like right here, and after that I have stripped off the photoresist. First of all I will be using a mask for the photolithography process at the particular location where I want the via trench. I will be using the mask and I will be removing the USG layer over that with the help of the mask, and then I will be stripping off the photoresist. Then I will be using the trench mask with the help of photolithography. I will be removing the trench. So this is called the etching of the trench. So you can see here I have etched out the trench and again I will be stripping off the photoresist. This is not required now. So after that we are going to do the PVD, the physical vapor deposition of the tantalum. So here we will be having the tantalum layer, a very thin layer for the barrier and the adhesion layer, because the copper is not very adhesive to this structure. So then after that I will be using the electrochemical plating of the copper. So here I will be having the bulk copper deposition and the seed copper deposition as well, and after that I am going to do the annealing, right? So after that we are going to do the chemical metallical polishing, so that I will be having the smooth surface over here, and we will be having the chemical metallical polishing of tantalum as well to get a better smoother surface over here. And then I am going to do the PECVD, the plasma enhanced chemical vapor deposition of the nitride layer. So here we will be having this nitride layer over all of these structures. So this is how we are finishing the copper metallization. So we are having the nitride seal layer which is preventing the diffusion of the copper outside, and it is also preventing the oxidation of the copper as well. So nitride seal is a very important layer that we have to deposit at the last, right? So we will be having the etch stop nitride which is going to separate the via and the trench etch. So tantalum is used as a copper barrier layer over here, right? So I have shown you where we were using the tantalum. It is used as a copper barrier layer. We are going to do the copper seed layer deposition with the help of the physical vapor deposition, and the bulk copper deposition is done with the help of electrochemical plating. We all know what is electrochemical plating. We have talked about the ECP in the previous lectures as well, and we have talked about ECP in the previous classes as well. In the class 11th we have talked about it. So now coming to the copper and the low dielectric constant dielectric material. So whenever I am using the low dielectric constant material with the copper, it is going to increase the speed further, right? So it is going to further increase the IC chip speed, and low dielectric constant dielectric material is still in R&D. We can use the alpha CF which is having the dielectric constant 2.5 to 2.7 which is less, and this can be preferred over here. It cannot be etched with the fluorine chemistry, and this is the disadvantage over here. It needs the oxygen chemistry to etch out the alpha CF. So we are having the new challenges for the process integration, because now I cannot use fluorine, I have to use oxygen, which is dangerous for the further steps as well. So you can see here we have the PECVD, the plasma enhanced chemical vapor deposition of the alpha CF over here, and then we have the USG layer, and then we have the via mask, and we are going to etch out the USG with the help of the hard mask. Okay, so here we will be having this USG layer and it is etched out over here for the via mask, right? After that we have the PECVD of alpha CF again, and then we have again the USG layer deposition, right? So you can see here we have the etching out of the alpha CF, and then we have the seal nitride layer. Okay, so when I etch out the alpha CF here, I have to use the oxygen chemistry, right? And this is going to hinder the upcoming processes as well. So here we will be having tungsten. Oxygen can go and react with the tungsten as well while removing out the alpha CF layer, right? So now you can see after that we are going to do the PVD of the tantalum. So here we have a very thin layer of the tantalum which can be deposited with the help of the physical vapor deposition. After that we have the copper seed deposition over here, and after that we will be having the bulk copper deposition with the help of electrochemical plating. Okay, so here you can see we have the bulk copper deposition right here. After that we are going to do the chemical metallical polishing of the copper as well as the tantalum. Okay, and now coming to the copper and the low dielectric constant material once again. I told you we require oxygen, and oxygen plasma is used to etch out the alpha CF. Now PR cannot last longer in the oxygen plasma. This is a very big disadvantage of using the oxygen chemistry to etch out the alpha CF. I cannot have a very highly sustained photoresist. So now here SiO2 hard mask is needed. This is again a disadvantage. Now oxygen cannot etch out the oxide and nitride, and for etching out the oxide and nitride I will be using some another molecule or compound, right? So this is again a disadvantage. So now trench and via can be etched at the same time, and we are having high selectivity of the alpha CF to oxide and the nitride. So now photoresist is removed when the oxygen plasma etch out the alpha CF, and now I don't want the photoresist to be removed, but in product of removing out the alpha CF, the photoresist is automatically removed, right? So this is again a disadvantage. Now coming to the passivation. After making the copper metallization of the copper interconnection or the aluminium interconnection, any type of interconnection that I want, after that I am making the passivation layer. The passivation layer is going to protect the chip from moisture and the other contaminants such as the sodium, so that these contaminants are not going towards the metallization part and it is not going to hinder any important functionality of the given chip. Silicon nitride is the most commonly used material to use it as a passivation layer. Now I can have the outermost covering of the silicon nitride which can easily protect the given IC from the moisture and the sodium ions. So usually oxide layer is used as a stress buffer, because whenever I am using the silicon nitride it is going to give a very high stress towards the chip which the chip cannot tolerate. So for a stress buffer I will be using the oxide layer. So SiH4 or silane based plasma enhanced chemical vapor deposition is done for both oxide deposition as well as the nitride deposition. So I hope you understood how we are depositing the oxide and the nitride passivation layer. So now here I will be using the bonding pad mask or the connecting bump mask to now connect it further to the packaging. Now here we will be using the fluorine based nitride and the oxide etching chemistry to etch out the passivation layer. So we can strip off the photoresist to finish the wafer processing at the last, right? So I hope you understood this process. So you can see here we are doing the metal annealing, right? So metal annealing is the high temperature process at which I am doing the annealing, which is making the structure single crystal once again after all of the processing. So you can see after that we are doing the PECVD of the oxide layer, that is plasma enhanced chemical vapor deposition of the oxide layer, right? After that we can do the PECVD of the nitride layer. So this is my passivation layer. So you can see after that we can do the photoresist coating, and then we can make the mask, that is the bonding pad mask, and then we can do the exposure and the development cycle, and then we can etch out the nitride, and this is how we can connect the packaging material with the metal interconnects over here, right? So this is how I am supplying the current from the outside world to the given metallic interconnect. So this is the metal 4 layer. With the help of metal 4 layer I am supplying the current. Okay, so after that I am going to strip off the photoresist. This is no longer required, and this is how here I will be having the passivation layer of the nitride and the oxide. So I hope you understood the process integration. We have understood a lot of things in the process integration unit. We understood how we can do the well formation, right? How we can form the isolations with the help of field oxide, with the help of local oxidation of the silicon, and with the help of the shallow trench isolation. We can form the sidewall spacer for lightly doped drain and for the salicide as well. How the sidewall spacer was helping me, this also we discussed. Now we talked about the aluminium and the polysilicon and the silicide for gate and the local interconnection. After that we talked about the tungsten, titanium and aluminium alloy, which are commonly used in the traditional interconnection processes, right? So I hope you understood all of them. After that we talked about the basic process step for copper metallization and the dielectric deposition, dielectric etch, metal deposition and the metal polishing as well. After that we talked about the passivation. There I talked about the importance of the silicon nitride and how it is the most commonly used passivation material in the IC processing. So this is the very important book which you can refer for your further studies, and you can put your doubt in the comment also. If you feel that you are not able to resolve your doubts from the books, you can put the doubt and I will be trying to resolve your doubt as soon as possible. I hope you like this session. If you like it, please push the like button, subscribe to the channel, share your important feedback with me about this unit, about this playlist as well, and share it with your friends. Thank you so much.